Welcome to Quantum Curious. In this lecture series, we will embark on an exciting journey into the world of quantum key distribution, QKD, a revolutionary technology that uses the principles of quantum mechanics to secure communication. So, in this first lecture, we will start with a brief introduction to QKD, what it is, why it matters, and how it's different from classical cryptography. Then we will dive into some foundational tools you will need throughout these lectures, including mathematical notations like complex numbers, bra-ket notation, and the concept of qubit. Let's get started. So, what is quantum key distribution? We have two parties, Alice and Bob, and they want to communicate with each other secretly. But there is a third party, a malicious party, Eve, that wants to listen into their conversation. So Alice uses her knowledge of quantum mechanics and came up with an ingenious and brilliant idea. She proposes that we can communicate with each other secretly by distributing a secret key with each other, and up the party or the person having this key can open the message secretly and safely. So she sends quantum states and encodes the random key into the properties of these quantum states and send it to Bob through quantum channel. Bob has a special detector that detects these incoming quantum states and decodes the information embedded into the quantum states. And they can assess the security of the whole procedure through classical channel. If the error is less than the threshold set by these two parties, Alice and Bob, they can go on with the communication and can use this key to to communicate the messages with each other. So you may be wondering that why we need this procedure as we have classical cryptography that works very well. So, in a future dominated by quantum computers, classical cryptographic methods may no longer be safe. QKD provides a way to secure our communications against even the most advanced attacks. So, formally, QKD can be defined as a secure communication method that uses quantum mechanics to ensure data privacy and detect eavesdropping attempts. So, to understand these kind of protocols of quantum key distribution, we need a special kind of language, the language of mathematics, and it usually involves the quantum information tools. So, in order to understand these things, we need to first review and have the knowledge of the quantum information tool, and then we can understand them properly. So we will start with mathematical notation. So our first concept in the mathematical notation is complex numbers. Uh, we know that complex numbers usually are associated with the numbers having the unit iota, and this is the square root of -1, and this belongs to the complex numbers. So we have, for example, a complex number that is c is equal to a plus iota b, where the whole number is a complex number, and where a and b are real numbers. And we can take the conjugate of the complex number or any complex number uh, by changing the aorta with minus aorta. And this alternate number is called conjugate of the original complex number. So we could see that complex number usually is represented by a graph having two axes. The y-axis is usually an imaginary axis, and the x-axis is usually a real axis. So we can see that we have a as a real number and b is imaginary number. Imaginary number in the sense that it is associated with the aorta. So we have the representation of the b on the imaginary axis and the representation of a on the x-axis. And The meaningful quantity, that is the absolute length or absolute value of the complex number, is usually calculated as the square root of the product of the complex conjugate and the uh, normal complex number. And it is usually written as the uh, sum of the squares of the two real numbers associated with the real axis and the imaginary axis. So the in linear algebra, the we can say that the mathematics of quantum mechanics or quantum information theory is the linear algebra. So we usually work with matrices and vectors, and these are the cornerstone of the quantum mechanical language. So we can define the vector space of complex numbers as collection of vectors with complex coefficients such that vector space V contains the all zero vector and is stable under vector addition and multiplication by scalars. So a vector space of dimension 2 having uh, vector V uh, can be represented by a ket vector, uh, or my or I mean to say that a ket vector in a vector space of two-dimensional can be represented by a column vector, and it has two coefficients, meaning it is two-dimensional column vector. So the corresponding conjugate vector is called the bra vector, or uh, it is obtained by the original ket vector by taking its complex conjugate, or you can say the complex transpose. And it is associated with taking the complex conjugate of the elements and taking the transpose of the column vector, and it gives us this row vector. So it is usually denoted as the dagger of a ket vector, and similarly, operationally calculated by taking the complex conjugate of the elements of the row vector or column vector and taking its transpose. So another interesting idea is the inner vector that we usually came up in usually encounters in we usually encounter in our quantum information theory. So consider we have two vectors from a complex vector space of dimension d, and we have d elements of each column vector, and we could take the inner product by changing the or by taking the complex transpose of the first vector v1 and multiplying it with a column vector. And this is just the sum of the product of the corresponding elements, like A1 complex conjugate is multiplied by B1, and then similarly A2 star multiplied by B2, and these all products are uh, sum up with uh, sum up with each other to get a complex number or a real number. So it is an interesting quantity. So another interesting quantity is or property of the vector space is a length of the vector space. So it can be calculated by taking, so consider we have a vector v in a d-dimensional vector space, and the norm or the Euclidean norm of the vector v can be calculated as the square root of the inner product or square root of the self inner product of the vector with itself. And this can be calculated similarly as the normal inner product. So from these things, we can uh, calculate the length of the vector, that is the meaningful thing of the vector. So usually a vector space has certain bases that span the whole space, and it depends upon the dimensionality of the vector space. And for example, we have two-dimensional vector space or three-dimensional vector space. In two-dimensional vector space, we have two axes, x and y axis, and the associated basis of the two-dimensional vector space could be the unit vectors associated with the x and y axis. Or similarly, we have three unit vectors or three bases in three-dimensional vector space. So using these bases, we can write or we can describe any vector in the given space. So we can generalize this idea of basis to d-dimensional vector space or b-dimensional vector space. Similarly, we have here a b-dimensional vector space, and all the vector spaces, all the basis of this uh, vector space are orthonormal to each other. And similarly, we can write the vector in terms of these spaces. So we know the idea of the bits, that is the reminiscent of the uh, uh, ancient, or the you can say the classical computer science. And we can describe a bit as a value that represents some information that is stored and manipulated by an algorithmic procedure. So bit is usually can be described physically if and only if we can differentiate it, like we are communicating with a through a fiber optics, and if there is no light signal, we can denote it as 0 bit. And if we have some light signal in the fiber optic, we can denote as the 0 bit. So we can describe the bit value associated with any physical phenomena. So for the communication purposes, we usually use the string of bits, and we can denote it as the n number of bits having 0 and 1.